Hello, friends. A very warm welcome to all of you to this session of Heat Transfer by the Gate Academy. So, I know you have already seen the title. So, we are going to talk about heat transfer from extended surfaces. You can note down the title, and this is a link. So, a bit.ly link is there. And from this bit.ly link, you can download the notes corresponding to the same. Hello, Neeraj. Good evening. A very good evening to all of you. So this lecture had to happen yesterday, right? But because of some technical glitch, actually we were not able to show the video. I don't know why this was happening. So we tried a lot for like 1 hour, but we couldn't do it. Hello, Akil. Hello, how are you? And Create Technology also a very good evening. So I think without wasting any time, we should start the topic. By the way, this topic is very important. So we are going to discuss the topic according to gate exam, IES exam, ISRO, DRDO, whatever. Okay. So all these exams, we are going to cover this topic. And please note, I will not go very deep into the topic because that might waste your time. You should right now you should focus on only that much quantity and quality which is required for the exam. Okay. So Create Technology, actually we are discussing more of gate exam today. So, and this topic is more important from gate exam. Definitely it's a part of SSC, but for SSC, formulas are more important. You might not require the derivations for your SSC exam, but today we will discuss derivations also. So let's start. So there are a lot of applications, examples, systems where we want to increase the rate of heat transfer from a solid surface to surrounding fluid. So can anyone tell me, if there is a solid surface and we have a surrounding fluid, what is the heat transfer mechanism between two? Anyone? Please be fast. Please be fast. There is a solid surface, we have a surrounding fluid, and we want the heat transfer mechanism between the two. I think it is convection, right? Solid surface, surrounding fluid, heat transfer will be by convection. Create Technology, it's convection, not radiation. Radiation is definitely there, but it will happen effectively only when the temperatures are very high, like in the range of 1000 degrees Celsius. But suppose my surface is at 100 degrees Celsius, water is at surrounding water is at 30 degrees Celsius, so convection will be more effective. Very good, Mandeep. Very good, Neeraj. For example, IC engine is there, compressors are there, AC refrigerators are there, motherboards are there, elephant and basically animals are there. So if I talk of IC engine, so during combustion a lot of heat is produced, है ना? And that heat is converted into work. But thermodynamics says that heat can never be completely converted into work. So definitely some heat will be left. Now that heat which is left, either it goes into the atmosphere in form of exhaust gases, or that heat is stored in the material of IC engine. Now suppose the temperature of the now consider the heat which is stored in the material of IC engine, that will raise the temperature of the material. If the temperature of material will become high, the hardness of material will reduce, and we know the piston is moving up and down, so there will be friction forces, there will be wear and tear. So if the hardness is less, the wear and tear will be more, and the life of the material will be less. Naman beta, this is not for civil engineering. This topic is only for mechanical engineering. I'm really sorry if there was a confusion regarding this. It's only a part of mechanical engineering. So if the heat is stored in the material of IC engine, temperature will rise up and the life of engine will reduce. So what we want is that heat should not store in the material of IC engine, it should go out, and definitely it will go out into the atmosphere by convection. So what we want is that from outer surface of the engine, we want to increase the rate of heat transfer to surrounding air. Similar is the case for compressors, pumps. Similarly, if you open the top front cover of an AC, you remove the front cover of an AC, you will see there are a lot of pipes. And around those pipes, you can see some ice, because in the pipes, cold refrigerant is flowing. But if you will see properly, that along with these pipes, there are lot of plates, very thin plates are there, and a very large number of plates are there. So you will see some kind of arrangement like this. Now here what we want is that some refrigerant is flowing inside, and there is some fluid outside. We want to increase the rate of heat transfer from the refrigerant to the outside fluid. But the refrigerant and outside fluid, they are again separated by a solid surface. So again there will be convection, so we want to increase that convection rate. Similarly, this is a motherboard. So for motherboard also, it's an electronic equipment. So when current will flow through that electronic equipment, there will be heat generated, and if heat generated stores in the motherboard, the temperature of motherboard will rise, and ultimately there will be some fuse and the circuit will break. So again, you want to increase the rate of heat transfer. Similarly, there are other applications also, like this elephant and this dinosaur, which you call as stegosaurus. So there are a lot of examples where we want to increase the rate of heat transfer. Now, can anyone tell me what is the what is the formula, what is the law which tells you rate of heat convection between a solid surface and a fluid? Anyone? Anyone? The formula which tells us. Anyone? The formula which tells us the rate of heat convection between the solid surface and the surrounding fluid? I think that is Newton's law of convection. So what we have is we have a solid surface which has an area A, and the temperature of the solid surface is Ts. Now this surface is surrounded by some fluid, and that fluid has a temperature Tf. So whether it is a forced convection, whether it is free convection, the convection can be written by Newton's law of cooling. And Newton's law of cooling says that Q dot convection, that is equal to HA into Ts minus Tf, right? This is the Newton's law of convection. Now, if you want to increase the rate of heat convection, so we want to increase this term Q dot convection. So there are three possible methods to do it. First one is to increase this temperature difference. So if you increase the temperature difference, Ts minus Tf, definitely the right hand side and therefore the left hand side will increase. But actually, Ts and Tf, they are mainly based on the application and the environment temperature. So you cannot alter it much. So for us, this Ts minus Tf is nearly the same. Similarly, if I talk of H, we can increase H also to increase the rate of heat convection. So what happens is that for free convection, H is comparatively less. So what you do is you install a fan and convert free convection into forced convection. Enough, the fan will give some velocity to the air. So when the air starts moving, the things get cooled down fast. So forced convection has more H as compared to free convection. So what you will do, you will increase H by installing a fan, by installing a blower. But that will definitely increase the cost of the system. That will definitely increase the weight of the system. So this approach might not be suitable. So increasing Ts minus Tf might not be possible, and increasing H might not be feasible. So there is only one possibility to increase the rate of heat convection, that is by increasing this area, right? Hana? And to increase this area, what they do is that on the solid surfaces, they add extensions like this. So if you drive a bike like a Pulsar maybe, so Pulsar is a naked bike, and you can see the engine of that naked bike directly. You will see that on the engine, on the sides of engines, there are some plates like this. And by the way, these plates do not have any mechanical function. I mean, in terms of strength, the only function is that these plates are extra areas, additional areas to increase the rate of heat convection. Similarly, these plates in air conditioners and refrigerators, these are extra areas to increase rate of heat convection. Whether you take a pump, whether you take a compressor, whether you take a transformer, on the outer body also of these devices, you can see these plates. Similarly, there is a motherboard. So on the motherboard, there is an equipment known as heat sink. It's a metallic equipment with some plates like these, with some fingers like these. So these fingers, they do not have any electrical function. Only function is to increase the area, so that to increase the rate of heat convection. Same is with the ears of this elephant and the plates of this dinosaur. So our ultimate aim is that if there is a solid surface, and if we add fins, if we add these extra areas on the solid surface, what will be the increase of rate of heat convection? This is what is the analysis we want to do, and that is what we are going to do over here. So firstly, we will discuss this, how to find out that if there is an extra area on a solid surface, what will be the rate of heat convection, and whether adding that extra area is useful or not. So this is what we are going to do. So in today's class, we will derive some formulas, we will see the derivation, and in the next class, we will use those formulas to solve gate type of questions, to solve IES type of questions. Okay, so let us start with our analysis. So there is no need, you can just write down that these extra areas, these extended surfaces for increasing the rate of heat convection, they are called fins. And what are the examples? IC engine, air compressors, pumps, motherboards, animals, lot of examples are there. So let us start with the analysis. And the analysis is actually very easy. So there is a very simple derivation is there, which will require a little differential equation. So even if you do not know the prerequisites, do not worry at all. I will tell you all the prerequisites and you can refer that to them at home also. Okay, so check. Hello Rahul, good evening. Hello Sachin, a very good evening. So what we have is, maybe this is the solid surface of an IC engine, okay, external surface of an IC engine. And this external surface has an area A and temperature Ts. This external surface is surrounded with a fluid Tf. Okay, any fluid can be there. This can be air, this can be water. The air can be at rest, the air might be moving. So any situation is possible. Now, what we want is that there is an additional surface, an additional material on this solid surface, which we call as fin. And the purpose of this additional material is definitely to increase the rate of heat convection between the solid surface and the surrounding fluid. Okay, so what you can do is you can mark a coordinate system over here. That is the x-axis. This will become the y-axis and this will become the z-axis. So our only objective is to see that how much there will be an increase in rate of heat convection. This is what we want to do. How much is the increase in rate of heat convection? And same kind of question is asked in your exams also. So what I have done is that to do my analysis, I have marked a coordinate system x, y, z. So if I see along the negative x-axis, negative z-axis, I will see a 2D figure, that is the xy plane. Okay, so here I have xy plane, and along the xy plane, this is your fin. Okay, now at x equal to 0, which is the joint between the fin and the solid surface, you can call it as base. You can call it as base, that is x equal to 0. And what we do is, I hope you can realize that yz, that is the plane of the surface. So x will be the direction perpendicular to the surface, है ना? So side of fin perpendicular to the surface, that is along the x-axis, we call it as length of the fin. So definitely the right hand side surface of the fin, please check the right hand side surface of the fin, you can mark it as x equal to L, and we will call it as tip. X equal to L, you will call it as tip. Now check, now check. Now things will start becoming easy. So please do not hesitate at all in asking doubts. So what we have is, we have a solid surface. On the solid surface, there is an extra material, and that extra material is exposed to fluid at temperature Tf. I think what will happen is that by conduction, the heat from the solid surface will enter into the fin. And by conduction, a part of heat will move towards the periphery, and definitely the remaining part will move ahead. Now the part of heat which reaches the periphery, that will go out into the atmosphere by convection. Is that right? है ना? From the solid surface, to the fluid, the heat will go by convection. And similarly here also, this part of heat will go into the atmosphere by convection, but it will move inside by conduction. Then like this, you can show the flow of heat in the entire material. So you can draw this figure in rough, and you can show the flow of heat inside the material and from the material to the surrounding fluid. I hope there is no doubt in this. But check. If I consider the flow of heat inside the solid material, that is definitely by conduction, है ना? And conduction can be solved by Fourier's law of conduction. Conduction can be solved by heat conduction equation, है ना? Now, what is your aim? Your aim is to calculate convection. But actually, here we will calculate convection by solving conduction. Please note, here I want to calculate what is the increase in rate of heat convection by adding this extra material. But I know that inside the material, heat is flowing by conduction. So for calculating convection, actually I will solve conduction. Do not worry, things will become very easy. So what we are going to solve? We are going to solve conduction in this extra material, and this extra material you call as fins. Okay. So I hope you remember that whenever we have to solve a conduction, what we do is we use an equation, heat conduction equation. And that heat conduction equation looks something like this. Del square T by del x square plus del square T by del y square plus del square T by del z square plus Qg dot by K is equal to rho C by K del T by del time. Okay. Now, those who do not know what is heat conduction equation, so you need not worry at all. Actually, heat conduction equation is an equation which relates temperature gradient. Temperature gradient means del T by del X, del T by del Y, del T by del Z with the temperature rate, that is del T by del time. So actually what this equation says is that suppose there is a point inside the material. Which material? The material through which heat is flowing by conduction. So there is a point inside the material, heat is flowing through the point by conduction, and definitely at this point, there will be some value of temperature. There will be some value of temperature, there will be some value of these derivatives also. So what this equation does is it relates these derivatives. And how do you write down this equation? Simply by energy conservation principle. So what you say, some heat will come inside the point by conduction, some heat will be generated inside the point by internal heat generation, and some heat will go outside. So you say energy coming inside minus energy going outside is equal to increase in energy. So this is how we write down this equation. It's very simple equation. Only thing is you should remember that whenever there is a problem of conduction, I will directly write down this equation. Once I write this equation, I will substitute my boundary conditions over here. And when I solve this equation within the material, I will get temperature as a function of x, y, z and time. So for every heat conduction problem, you use this equation. And when you solve this equation, you get temperature in the material. Temperature at any point in the material. This is what the equation gives you. And then using Fourier's law of conduction, you can find out the heat transfer rate. So Fourier's law of conduction says minus K del T by del X, something like this. So if you do not have an idea of these equations, I would suggest you that please look into the conduction chapter. These two equations are very important, and any problem of conduction is actually solved by these two only. Any problem, nothing else you have to use in any of the equations. Okay. So heat conduction equation and Fourier's law of conduction. This is what we are going to use over here. So what I will do is I will take a point inside the material, write the heat in conduction equation for that point, and find out what is the temperature in the material. Now, once I get temperature in the material, I will substitute it here. And once you substitute it over here, you will get the heat conduction rate. So from here, we are going to find out the heat convection rate as well. Okay, so I think we should start now. So let us see what are the assumptions of our analysis. So these are the notes for the same topic, this bit.ly link. You can use it, okay? So let us write down the assumptions one by one. So first of all, the very important assumption that is actually possible. First assumption is that we are going to talk about steady state system. We are going to talk about steady state system. So I hope you remember steady state means that nothing is a function of time. Temperature is not a function of time. So if temperature is not a function of time, this means del T by del time will be 0, right? This is the very first assumption. Definitely inside the fin, there cannot be any internal heat generation. So internal heat generation will not be there. So we will write down no internal heat generation. No internal heat generation. So if I talk of heat conduction equation, in that equation, the second point is represented by Qg dot. So that Qg dot will be 0. So this Qg dot will be equal to 0. Then if I talk of the next assumption is that material is homogeneous. So if material is homogeneous, then you take 2 points inside the material. On the 2 points, the thermal behavior will be same. So for those 2 points, thermal conductivity will be same. So what we have is we have homogeneous isotropic material. So here you can write down homogeneous isotropic material. So the problem which I am going to solve, in that problem, there is no requirement of isotropy. I mean, our solution does not depend upon isotropy. But just for your information, you should check what is the meaning of isotropy. So this is your homework. What is the meaning of isotropy? Now, next point. So actually what happens is that if this is the length of the fin, then this side will be called as B. Let us call it as width. And this side will be called as T. This is thickness. Okay. So this particular area, which is parallel to plane of solid surface. So this cross section, this is called as cross section of the fin. This is called as cross section of the fin. And this front view, this front view is actually called as profile of the fin. So please note there are two things. So if you talk of YZ plane, that is the cross section. Please check what is your YZ plane. YZ plane. So B and T. B and T, they are the cross section. But if you talk of L, and T, that is the profile. Now here I have shown you a fin of rectangular cross section, but your fin can have circular cross section also. Say for example, this is a circular cross section fin, right? This is a circular fin. There can be a triangular fin also. Okay, so cross section is circular, cross section is triangular. So this is circular pin, pin fin, that is triangular fin. Okay, so different kind of cross sections are possible. Similarly, let us suppose our fin is tapered. So when you say tapered fin, say for example, this is the fin on the solid surface. This is the fin on the solid surface. So I hope you can see that as you move along the x direction, the cross section of the fin decreases. As you move along the x direction, the cross section of the fin decreases. So we call them as tapered fins. But here, if you check the cross section at the base, if you check the cross section at the base, or you check the cross section at the tip, both the cross sections are same. So this fin is non-tapered, है ना? So non-tapered fins are called rectangular profiles. What kind of profiles? Rectangular. This is a triangular profile. Please note, for this, the cross section is rectangular only, but the profile is triangular. Okay. So in our analysis, we are going to take a rectangular profile. What kind of profile? Rectangular profile. But rectangular profile means that the cross section at the base is same as cross section at the tip. Cross section at the base is same as cross section at the tip. However, that cross section can be circular, that cross section can be rectangular, cross section can be triangular also. So okay, so this is one more assumption. So you can say rectangular profile or uniform cross section. Rectangular profile or uniform cross section, both have the same meaning. Okay, now what happens is, suppose the fluid is moving, so this fin is exposed to air. So if I talk of a bike maybe, so when the bike moves, so with respect to the engine, the air moves in the backward direction. So with respect to solid surface, the air is moving. Now check, some air will be moving over here and some air will be near the tip. So when we talk of air near the base, it is exposed to two surfaces. One is the solid surface, other is the fin. So when the air is exposed to multiple surfaces, friction forces will be more and air will be slow. If air is slow, H will be less. So when I talk of air near the solid surface, H value is less. But if I talk of air near the tip, that air is moving freely. So H value will be high. So actually what happens is that for the fin surface, the coefficient of convection is less near the base, but coefficient of convection is more near the tip. So coefficient of convection is actually varying along the x direction. But that thing also we will not consider. We will consider that coefficient of convection is uniform entirely. Okay. Thank you, Arjun. Thank you so much. So coefficient of convection is uniform entirely. Coefficient of convection here is same. So one more assumption will be there. Uniform H. Everywhere the coefficient of convection is same. So these are the assumptions that we are going to use. So please note down the assumptions and then I will rub it. Please note down the assumptions fast. Definitely, this topic might be a little typical for those students who have not done conduction, but what they can do is they can note down, they can take notes from the lecture, and when they do the conduction, they can refer to same notes. In case of any doubts, you can ask doubts in the comment section also. Okay, so these are the assumptions. Now the question is how to solve it. So I told earlier also that even though we want to find out the heat convection rate, but actually we are going to solve conduction inside the material. Acha, by the way, I missed one very important assumption. One very important assumption I missed. That important assumption is that we are going to assume that temperature inside the fin is a function of X. Check, just now a few minutes back you guys only told me that if I take a point inside the material, definitely from this point some heat is going towards the tip and some heat is going towards the periphery, है ना? So heat is not only flowing along the x direction but along the y direction as well as z direction, and heat only flows along the direction where the temperature decreases. So temperature is decreasing along x, temperature is decreasing along y, temperature is decreasing along z. So if I consider inside the material, temperature is a function of x, y, and z. So definitely this is 3D heat conduction. But I am going to assume the temperature is only a function of x. So I will consider only one-dimensional heat conduction. You know why? Because I do not know how to solve 3D conduction. Okay, it's difficult. Partial differential equations are difficult for me. So I will solve only one-dimensional heat conduction. So I will assume that inside the material, temperature is only a function of x. Okay, temperature is not a function of y and z. Please note down this sixth assumption. It is a very important one and I forgot it. Okay, so let's see how to do it. So I hope you remember that and you have learned in your semesters also, or maybe in your coaching classes also, that whenever we solve conduction, we want to find out what is temperature as a function of x. When you are solving planar wall, so you try to find out what is the temperature at every point. If there is a planar wall with internal heat generation, so you try to find out what is the location of maximum temperature and what is that maximum temperature also. First of all, location of maximum temperature and maximum temperature. So you want to find out T as a function of X, right? This is what you are doing in every problem. The same thing we are going to follow here also. We are simply going to say this is X equal to 0, okay? This X equal to 0 is the point where the fin is attached to the base. So definitely here the temperature will be same as temperature of the base. So let us say it is Ts. So at x equal to 0, the material temperature is Ts. So we want to find out that if there is a distance x and at distance x there is a section, what is the temperature of this section? This is what we want to find out. Temperature of the section which is at a distance x, T as a function of x. This is what you want to find out. So what you will do, inside the material you will take a point. For the same point, basically this point, inside the material you will take a point, the point which is at a distance x. And for the point, you will write down conduction equation. So please note down your conduction equation: del square T by del x square plus del square T by del y square plus del square T by del z square plus Qg dot by K is equal to rho C by K into del t by del time. I know it looks boring, but actually this equation is very magical. And in fact, this equation is telling you everything. This equation will tell you everything, not the equation, basically the procedure of writing the equation. The procedure of writing the equation tells you everything. Okay. So for this particular case, we know temperature is not a function of time because we are solving steady state system. So I think this side will become 0, right? Now the internal heat generation is not there. So Qg dot will also become 0. Temperature is only a function of x. It's not a function of y and z. So del square t by del y square will be 0. Del square t by del z square will also be 0. So only one term is left. See, now the equation looks so easy. So what we have? We have del square t by del x square equal to 0. So based on this, since temperature is not a function of y, z, time, it's only a function of x. So I hope you remember, when any quantity is only a function of x, then partial derivative and total derivative are same. Okay. So you can write this partial derivative as total derivative also. So d square t by dx square is equal to 0. This is the differential equation. This is the differential equation for solving temperature as a function of x inside the material. Why I'm saying again inside the material? Because please note, I have written the equation of conduction, है and it is inside the material that conduction is going on. So conduction outside the material, convection is going on. I'm talking of inside the material. Prabhat, beta, actually, I'm not sure about the schedule of manufacturing, but suppose if schedule is not there from our side and you want manufacturing to go on, then definitely you can mail us. Okay, so info at the rate thegateacademy.com, quality at the rate thegateacademy.com. You can call them to tell them that manufacturing ka live lecture lagao. And you can call this number also. This is not only for admissions, but for lectures also, okay, for your feedbacks also. And in fact you can give feedback also, whether we are teaching good or we are teaching bad, so everything is possible. So this equation will tell you temperature as a function of x. Now check, so when we write down temperature as a function of x, I think you integrate once. So once you integrate, dt by dx will be equal to c1x. Dt by dx will be equal to constant, right? Integral of 0 is a constant only. And when you integrate again, this will become t equal to c1x plus c2. So temperature is equal to C1x plus C2. So what is this? This is the temperature at this point. The temperature at the section which is at a distance x from the base. Okay. So any conduction problem is solved like this. You use the heat conduction equation, you put the assumptions in the heat conduction equation, the differential equation which you get, है ना? See, heat conduction equation, you put assumptions in heat conduction equation, you will get a differential equation, you solve differential equation, you will get temperature as a function of x. So we simply want to find out what is temperature as a function of x. But the point is, this is wrong. In this particular case, we are getting something which is not right. Let me show you how. Okay. So t is a linear function of x. है ना? T is a linear function of x. So when I talk of dt by dx, that is a constant. So dt by dx is a constant. This means it is not a function of x. Dt by dx does not depend upon x. Now check. Suppose I take two sections, one at a distance x1 and another section at a distance x2. Okay, so I have drawn two sections, one at a distance x1, other section at a distance x2. Okay, so basically we are talking of an element like this. This is section x1, this is section x2. Okay, now check what is happening over here. So when I'm talking of this element, definitely some heat is coming inside the element from the material, right? By conduction. And similarly, some heat will go outside by conduction. है ना? Bhaiya, what will happen? Here the temperature will be high. Here the temperature will be lowest. So definitely heat is flowing inside like in this direction. है ना? So what is happening? Some heat is coming inside at section 1. Some heat is going outside at section 2. And also the periphery of the element, peripheral side of the element, that is exposed to atmosphere. So there will be some convection also. है ना? So what we have is some heat is coming inside the material by conduction, some heat is going outside the material by conduction. These directions, how can I say the direction? Here the temperature will be highest, here the temperature will be lowest. And also there is a convection. Now check, the system is at steady state. So if the system is at steady state, this means whatever energy is coming inside the element, same energy will go outside the element. Now check. So what I will say, energy coming inside the element, which is Q dot 1. So this energy coming inside is equal to energy going outside the element. So this will be equal to Q dot 2 plus Q dot convection. है ना? So Q dot 1 is equal to Q dot 2 plus something. So definitely Q dot 1 and Q dot 2 are not equal. Okay. Now check. By Fourier's law of conduction, Q dot 1 will be written as minus Ka dt by dx for section 1. है ना? So minus K for section 1, A for section 1, dt by dx for section 1. And similarly, Q dot 2 will be written as minus Ka dt by dx for section 2, right? Now check, K is same because homogeneous material. Area is also same because we are talking of rectangular profile. Now what about dt by dx? Now check, dt by dx is a constant. So everywhere dt by dx is same. So dt by dx for section 1, dt by dx for section 2, they are same. है ना? This means q dot 1 should be equal to q dot 2. But physically, q dot 1 is greater than q dot 2 because of this convection. So if we are solving by heat conduction equation, what we are getting is that q dot 1 is equal to q dot 2. But physically, q dot 1 is greater than q dot 2 because of this convection. So definitely there is something wrong. Something wrong we are getting. And actually, this wrong result is not because of heat conduction equation. Heat conduction equation is always true. It always gives the correct result. Why we are getting a wrong result? That is because of a wrong assumption. We are getting a wrong result because of wrong assumption. And what is that wrong assumption? The temperature is only a function of x. But actually inside the material, temperature is a function of x, y, as well as z. So actually our assumption was wrong. And why I took this assumption? Because I cannot solve the three-dimensional problem. So if you are taking a simple assumption and you are not getting results from heat conduction equation, then definitely you should use some other method. है ना? So particularly in fins and also in lumped parameter analysis, we do not use heat conduction equation. We use other method of solving it. Okay, so please remember that particularly in fins, particularly in lumped parameter analysis, and the case of variable cross section. I hope you remember planar wall, variable area of cross section. So in these three cases, you cannot solve conduction by heat conduction equation. Not because heat conduction equation is wrong, actually because our assumptions are wrong. So you need other methods. So we will see what the other method is. So for now, what you will do in your copies, you will do like this. This method is wrong. Okay. So please do not solve fins by heat conduction equation. So let us see what that other method is. Okay. So let me rub it down and we will see that other method. It's a very easy method. So no need to worry at all. So what we will do, we will try to derive something and we will continue with the remaining derivation tomorrow. So hardly in the next class, in the next class, not tomorrow. I think the next class on the same topic is day after tomorrow. So in the next class, we will complete the formulas and we will discuss the questions related to it, like the type of questions that can come. And in case of doubts, you can mark those doubts in the comment section so that I can reply to your doubts also. Otherwise, those students who are like associated with us, they can contact directly also. Those students who are watching only this video, they can put doubt in the comment section. So let us see what the other method is. So this is your fin. Please note, I'm showing only the 2D figure. I hope there won't be any problem. We will be able to make out in 3D also. So what we have is, this is the base, x equal to 0. And this is the tip, x equal to L. Okay. Now I know that inside the fin, heat is flowing along this direction. And definitely some heat is going towards the periphery also and then getting convected. But we are assuming that temperature is only a function of x. So let me do one thing, that in heat conduction equation, what is the procedure? The procedure is to take a very small element, that is a point element. And for that point element, we write down the energy conservation principle. Heat coming inside by conduction minus heat going outside by conduction plus heat generation, that is equal to change in energy. So here also we will do the same. But here, instead of taking a very small element, I will take a bigger element. So what I have is at distance x, let us say there is an element, big element. Big element means it covers the entire thickness, entire width of the fin. Big element means it covers the entire thickness and entire width of the fin. But the thickness of the element is very small and its thickness is dx. Okay. So basically this element is made of two sections. One section is x, and the other section is x plus dx. I hope there is no doubt in it. And let us say that the temperature of this element is T. So basically T is the temperature of element at a distance x. Which element? The element which extends along the entire thickness of fin, entire width of the fin. But thickness of the element is negligible. Dx is very small. Okay. Now inside the material, we know that heat is flowing by conduction. And the peripheral side of the element is exposed to environment. So there will be some heat convection. Now check. There are two sections, section x and section x plus dx. I think based on general direction of heat flow, from this side, the heat is coming inside, and from the other side, the heat is going outside. So I will write it as Q dot for section X, which is coming inside. Q dot for section X plus dx, which is going outside. And this I will write as heat convection rate, Q dot convection. Uh, Hi, Dinesh. Dinesh, actually, right now, I'm not sure about the complete series is being put or not, but we will discuss some important topics which are like a little different from the remaining topics from the mainstream syllabus. Like I will discuss fins. I will discuss lumped parameter analysis in next pair of classes. Similarly, I'm thinking of discussing view factors for radiation because that is also important. Maybe I'll discuss critical thickness of insulation. So those topics which are important from heat transfer point of view, those topics we will try to cover. Anyways, thank you for asking. Huh. So we were trying to figure out this element. We were looking at what are the energy interactions for the element. Now check. Some heat is coming inside by conduction, some heat is going outside by conduction, and some heat is going outside to the atmosphere by convection, but the system is at steady state. So whatever energy comes inside, the same energy goes outside. So let me check what are the energies coming inside, Q dot X. What is the energy going outside, Q dot convection, Q dot X plus dx. Okay, so what I will do, I will write Q dot X is equal to Q dot X plus dx plus Q dot convection. Please note Q dot X, Q dot X plus dx. These are conduction terms, conduction inside the material. And that term is convection, convection from the peripheral area. Okay. So let us see what that peripheral area is. So if I will draw the element, I think the element will look like this. This is the element in 3D. This is T, this is B, this is dx, right? Now, this section is inside the material only, where we are getting conduction, x plus dx. Similarly, the left-hand side is x inside the material where we are getting conduction. But the front surface, this one, the top surface, this one, the back surface, and the bottom surface, these four surfaces of the element are exposed to atmosphere. So this is the peripheral surface. Now let me check what is the area of this peripheral surface. So check, this is T, this is dx. So this front area will be TDX. Similarly, back area will be TDX. If you talk of top, this is B, this is dx. So this top area will be BDX. Similarly, bottom area will be BDX. So what is the total peripheral area? Total peripheral area is top plus bottom, that is twice BDX, plus front plus back, that is twice TDX. So this becomes twice of B plus T into dx. Now anyone can tell me what is twice of B plus T? What is twice of B plus T? Please check. Please check what is twice of B plus T. I think this is B, this is T. So twice of B plus T is nothing but the perimeter of area of cross section. Hai na? It is the perimeter. Very good, Arjun. This is the perimeter. So we are talking of perimeter, PDX. So total peripheral area is PDX. And the temperature of this element is T. So basically this peripheral area, this has temperature T. And what is surrounding fluid? Surrounding fluid is TF. So from this peripheral area, the rate of heat convection will simply be equal to H into area, which is PDX, into temperature of area, which is T, minus temperature of fluid. So this is the rate of heat convection from the element. So basically Q dot convection you have written. You have written Q dot convection. Please note this down. Okay, so I think you have noted it down. Now check. Let us solve these conduction terms also. So I think I can write this as q dot for section x minus q dot for section x plus dx equal to q dot convection. But q dot for section x minus q dot for section x plus dx. Remember Taylor series. Try to remember Taylor series. When the variable is x, the function will be f. And when the variable is x plus dx, the function will be f plus del f by del x dx. I hope you remember this. Taylor series expansion. Similarly, when the variable is x, the function is q dot. What will be the function when variable is x plus dx? Hai. So what I will do is I will use Taylor series on this rate of heat conduction. Taylor series on rate of heat conduction. So this will become q dot for section x minus q dot for x plus dx. So that will be q dot plus del q dot by del x dx. So this is equal to q dot convection. Please note q dot is heat conduction. Heat conduction is given by Fourier's law. So if you will solve this, q dot and q dot will cancel out. So you will have minus del q dot by del x dx is equal to q dot convection, which is already written over here, hp dx T minus Tf. T is the temperature which we want to find out. Okay. So I think I'll rub this. Now, please remember Fourier's law. So Fourier's law gives you the heat conduction rate. Fourier's law gives you the value of q dot, and q dot is minus Ka dt by dx or del t by del x. So this you will write as negative of del by del x of minus Ka del t by del x. So this is q dot by Fourier's law into dx is equal to hp dx T minus Tf. Okay. Now check. So minus and minus will cancel out. Dx and dx will cancel out. And since t is a function of x only, so partial derivative can be written as total derivative. Also, whatever may be the value of x, we have a homogeneous material. So everywhere thermal conductivity is same. So thermal conductivity is a constant. Also, whatever may be the value of x, we are talking of uniform cross section, rectangular profile. So everywhere area is same. So for us, k and a are same. So k and a are constants. Hai. So once constant, these will come out of the derivative. And partial derivative, I will write as total derivative because t is only a function of x. So I will have ka d square t by dx square, and this term I will bring on the left hand side. The right hand side I will bring on left hand side. So I will have minus hp t minus tf equal to 0. And just to make this differential equation more beautiful, more simple, we will do one thing. We will divide the entire equation by ka. So please note this down. This is the procedure for finding out temperature as a function of x inside a fin. So what we have is, we have d square t by dx square minus hp by ka into t minus tf equal to 0. So if we solve this differential equation, we will get t as a function of x. If you solve this differential equation, you will get t as a function of x, right? Now, the question is how to solve this equation. And the best part is such kind of equations you see in theory of machines also, vibrations. Such kind of equations you see in fluid mechanics also, flow through pipes. Please check over there. You will see such equations. Say, for example, if I talk of vibration, there you have this equation, d square x by dt square plus omega square x equal to 0. Here, the dependent variable is x. Independent variable is time. Hai. So d square x by dt square plus omega square x equal to 0. And here the dependent variable is temperature. Independent variable is x. So same kind of equation. So I hope you remember x is an exponential function of time, something like this, if you remember properly. And what you do is, since those exponential functions, they are e raised to power I omega t, then you write down sine and cosine. Okay, please check vibration also. So let me show you how to solve such kind of differential equation, and it's very easy. So just to make the differential equation simple, let us write t minus tf as theta. Okay, let us write t minus tf as theta. And what is T? T is the temperature for section X. T is a function of X. So when T is a function of X, theta is also a function of X. है ना? So here you can say T is a function of X, theta is a function of X. So you will have dt by dx is equal to d theta by dx. है ना? Derivative of constant, Tf is a constant, Tf is the atmosphere temperature. Whatever may be the value of X, Tf is the atmosphere temperature. It's a constant. So dt by dx equal to d theta by dx, or d square t by dx square equal to d square theta by dx square. So your final equation will be d square theta by dx square minus. Now let me do one thing. You have that term na omega square. So let me do one thing. Let me say hp by ka under root, this is equal to m. Okay, why I'm doing this? Because I know that h is a coefficient of convection, a constant for me. P is the perimeter of cross section, again a constant for me. K is the thermal conductivity, constant. A is the area of cross section, constant. So I'm writing it as a constant. So root hp by ka, that is m. So this becomes m square. So you will have m square into theta equal to 0. Now it looks like d square x by dt square plus omega square x equal to 0. It looks something like this. Now solving it is more easy. So let us see what that solution is. Please guys note down fast. If you are noting it down, please note it fast. And same kind of stuff you will find in these notes also. Please, so this bit.ly link you can note down if you want the notes. So the notes do not have questions, but they have complete theory. And these notes I have written them on the basis of content in Cengel and Incropera. Okay, so they are only related to GATE and IES syllabus. Yes. So SK, beta, when I started the class now, then I showed. Then I just had a small discussion that how h is a function of x. But we are assuming that h is not a function of x. So we are treating h as a constant. Okay. H definitely is a property, but h depends upon the fluid flow. So if the fluid flow is slow, h will be slow. If fluid flow is fast, h will be higher. So what happens is that near the base, the flow speed is less. So h value is less. So it's like this. H is a function of x in actual, but we are treating h as a constant. Now let's see how to solve this equation. So we want to find out solution of the equation. So basically you want to find out function theta. You want to find out function theta which satisfies this equation. Now check, it's very simple. I think I can write d square theta by dx square equal to m square theta. है ना? So what it says, bhaiya, you derivate theta 2 times, you will get theta multiplied by a constant. You derivate theta 2 times, you will get theta again multiplied by a constant. है ना? This is the type of function. Theta is such a function, you derivative twice, you will get theta again. है ना? So check. Suppose there is a variable y which is an exponential function of x and you derivate it twice. So I think I will have d square y by dx square equal to a square e raised to power ax. है ना? So when I derivate y twice, I'm getting y again multiplied by a constant. So this is the property of exponential functions, है ना? So this means theta is also an exponential function. Vijay, beta, this is a live, and today we have started with fins. So I'm just showing you how to derive the formulas for fins. Okay. So theta is an exponential function, है ना? Derivate theta twice, you get theta multiplied by constant. You derivate exponential function twice, you get exponential function multiplied by constant. So theta, that is t minus tf, is an exponential function. So definitely theta is an exponential function. But the question is, what kind of exponential function? Hana? This is what the question is. What is the value of a in this? Hana? This is what our question is. So check. So if theta is the solution, if theta is the solution, theta should satisfy this equation. Hana? So I will put theta over here. So I will have d square by dx square of theta. So I will have a square e raised to power ax. Please note, I have put theta over here and you have double derivative. So that will become a square e raised to power ax. This should be equal to m square theta. So this should be equal to m square e raised to power ax. So e raised to power ax, e raised to power ax cancels out. This means a square equal to m square, or a is equal to plus minus m. So when the value of a is equal to plus minus m, when the value of a is equal to plus minus m, then theta satisfies the differential equation. Theta is the solution of differential equation. Okay. So what is theta? Theta is either e raised to power mx or it is e raised to power minus mx. This is theta as a function of x. Okay. So I hope it is understood. If anyone has a doubt, they can ask in between. Okay. Please ask in between if there is a doubt. So theta is a function of x, e raised to power mx or e raised to power minus mx. Now again go to the theory of differential equations. So in differential equation it says, Bhaiya, if a function has two solutions, if a function has two solutions, then linear sum of two functions is the final solution. Linear sum of two solutions is the final solution. Some kind of theory like this is there in differential equations. So what I will say, theta is equal to e raised to power mx, one solution, one solution. Theta is equal to e raised to power minus mx, another solution. Then final complete solution is the linear sum of two. Okay. Final complete solution is the linear sum of two. So theta is equal to constant e raised to power mx plus constant e raised to power minus mx, where c1, c2 you can call as constants of integration. So what is theta? Theta is t minus tf. So finally you have t. T was function of x. Finally you have t minus tf equal to c1 e raised to power mx plus c2 e raised to power minus mx. So you have solved one point. What is that point? Temperature as a function of x. So it is some kind of exponential function. Okay. So one objective we have solved. And through this objective, ultimately we will find out what is the rate of heat convection. Okay. So till now, any doubt is there? Any doubt you guys want to ask? Any doubt you guys want to ask? Okay. So today the class was planned for 1 hour. So what you can do is this video will be, I think it will be uploaded again on YouTube only. So watch this video again. And tomorrow from here only I will continue. Till now, I have not solved my objective completely. My objective is what is the rate of heat convection from the fin. But I am solving what is temperature inside the fin. Hai. Actually, this will help us arrive at our conclusion. And only like 5-10 minutes step is left out. So tomorrow we will continue with this equation. We will see how to find out C1 and C2. Once you know C1 and C2, you will get complete temperature as a function of X. Now that temperature as a function of x, we will substitute in Fourier's law of conduction. And through Fourier's law of conduction, you can find out heat conduction rate. But heat conduction rate will give you heat convection rate. Okay. So this is what we are going to do. So like 15-20 minutes we will spend on theory and remaining 45 minutes or maybe 1 hour also. Matlab tomorrow it can be a little extended. It instead of 1 hour, it can become 1.5 hours because I want to discuss all type of questions. So SK is asking book. SK beta, actually I've initially when I started teaching, I would think that this book is better, this book is best, but now I feel that every book is like beautiful, and it has a lot of efforts in it. So particularly for GATE exam, DS Kumar is a good book, very good book, simple language, all type of questions. Okay, and why I'm suggesting you this, because you do not have too much time to cover all the syllabus, है ना? So right now, DS Kumar is a sufficient book, sufficient theory, sufficient number of questions, all kind of objective points. So that is sufficient. Otherwise, those who are if someone is there who is doing research, for them I would suggest that you read Sengel first, then you read Incropera, and then some other books are there like Robert Seigel and others. So for now, DS Kumar is sufficient. Anything else? Anyone? SK, Dinesh, Arjun, anyone? Vijay? Anyone? If someone wants to ask a doubt, they can do it. If not related to this topic, any other topic of heat transfer, create technology, Neeraj Kumar, Rohit Singh, any doubts? RK Rajput is also fine. RK Rajput is also fine. So particularly in DS Kumar and RK Rajput, there are few points in convection chapter which are a little wrong. Those in dimensionless parameters, and particularly related to thermal boundary layer. But I don't feel that that is going to affect you in the GATE exam. Also in radiation chapter, some mistake is there in reciprocity theorem, but that you can defer to the notes. So when I will derive view factor na, so next class will be on lumped parameter analysis, and maybe next week or within a few days we will bring view factor also. So in view factor I will show you what is the exact reciprocity theorem. Otherwise both books are good. For GATE exam they are sufficient. Okay, so shall we stop? So please revise this once, and you can also have a look in your books. If you have books, or if you have notes, you can see the further content, and in the next class you can discuss the further content with me. Thank you very much. See you tomorrow. I mean next class. See you in the next class, day after tomorrow. Thank you.